Okay, in the last video we were looking at the fact that Newtonian mechanics was incomplete and what would be required to replace it. So let's get to the crux of the issue of what's incomplete with Newtonian mechanics, and that will involve us reviewing the Galilean transformation. That's those problems that you're doing back in mechanics that were like a dog is swimming down the river and the river is going so fast. How fast does a person say the dog is going relative to the shoreline? That kind of a problem. So for our purposes, we will always have two observers, and the physics community has always decided that they're named S and S prime. Usually, you will say that S is the one that the narrator of a problem thinks is moving, or sorry, thinks is stationary. One that the narrator thinks is stationary. And S prime conventionally is the one that the narrator of the problem thinks is moving. Again, conventionally, we will say that at t equals t prime equals 0, the origins overlapped. And we usually say that S prime is moving along S's x-axis. And we also will agree that the coordinate axes that S prime and S have are parallel to each other. Now, if we need it to be rotated, or we need the times to not match, or we need the origins to not perfectly overlap, or whatever, we can always cope with that, but that's just an additional complication that we don't really need. So we'll go with this. So now let's imagine a firecracker explodes. So in classical physics, both S and S prime will agree that happened at the same time, although that's an assumption we'll have to revisit. But let's just assume it's happening in the so we'll say at S, we'll measure it happening at x, y, z. S prime will measure the same thing happening at x prime, y prime, z prime. Now, because S prime's motion is parallel to S's x-axis and vice versa, they'll agree on the y and z coordinates for the firecracker. They'll both agree that, so y prime, the value that S prime measures for the y coordinate, will be the same as the y, the value that S measures for the y coordinate, and same for the z coordinates. But what about the x coordinate? Okay, now here we're going to measure two different things. So S is going to say that the x coordinate is this distance here, and S prime is going to say it's just that distance there. Well, how much do they differ by? They differ by the distance between the origins at this later time. So this, how much distance is that? It's the speed you're going times the time. So we can conclude that what S prime will measure is x prime. The x coordinate S prime measures will be the x coordinate S measures, x without the prime, minus vt. And if we need to go the other way for some reason, we would note that x is equal to x prime plus vt. All right, well, that's all good. But now let's say instead of just having a firecracker exploding somewhere, we instead say have somebody throwing a baseball or something like that. So now, in order to not be confused, we conventionally will say that u is the velocity measured by s, and u prime is the velocity as measured by s prime. Okay, and how are these related? Well, the x-coordinate, both of them will measure x-coordinates, and they will be continuously changing. So we can just differentiate. So we can say dx prime dt would be let me make that a little cleaner to read. Will be equal to dx dt minus v. But dx prime dt is our velocity u prime as measured by our observer s prime. And same thing with dx dt, that'll be the velocity u as measured by s. So we get that the velocity measured in s prime's frame will be the velocity measured in s's frame minus the velocity of s prime with respect to s. And again, if we're going in the other direction, we would say that u is equal to u prime plus v. General rule of thumb with these transformations is if you need the inverse transformation, the way I usually remember is to say change the primes, change the signs. Okay. But now let's say instead of our baseball just moving at a constant velocity, let's say somebody's pushing on it, so it's feeling, someone's exerting a force on it. Okay. Well, if someone's exerting a force on our baseball, then it would also be the case that it would be undergoing an acceleration. And potentially these should have, it's quite possible that s prime and s won't measure the same acceleration. So let's go ahead and figure that out, whether they do or not. So we can get the acceleration that s prime measures. We can just differentiate this with respect to time, right? So du prime dt, differentiating this with respect to time is just du dt, and since v is a constant, it drops out of the derivative. And so we're left under the Galilean transformation that both observers, even if they disagree on the speed, on the velocity of the ball, they both agree on its acceleration. And because of that whole F equals ma thing, and we'll have to think about that more carefully in a bit as well, we get that they also agree on the forces that something feels. So that's recapping what we saw before in mechanics with the Galilean transformation. So we're going to be needing this. So here, this bit here where a prime is equal to a, f prime is equal to f, we call those invariants. Under the Galilean transformation. That's just a fancy way of saying that all observers agree on what those values are. Okay. Let's see if we can find some more invariants, and while we're at it, let's think about how we would measure length. So sit and think carefully. How do you measure length? I mean, like, for real. I mean, I know you're going to say, yeah, you pull out a meter stick, but let's say you're measuring the length of some rod here, something like that. When you're reading the meter stick, what condition do you have on the readings? You have to measure the x-coordinate on the right end, you have to measure the x-coordinate on the left hand, right? On the left end, and you're going to get that the meter stick length is equal to x2 minus x1. But what condition do you have on the observations of the x-coordinates? So pause the video and think about that one for a second, and we'll loop back on that. Alrighty, so hopefully what we've agreed on is that both of these had to be measured at the same time. I mean, if this is moving along at some speed v over here, if I would first read x1 and then read x2, the whole thing would have slid along, and then I'll read a different value for x2, and if I just do x2 minus x1 there, then I'm going to get a value that's too long for it. So you have to make sure that they're read at the same time. So what we can imagine is that we have simultaneous firecracker explosions. So these both happen at the same time. And then we can go ahead and get that our L is x2 minus x1. All right, now let's think about how this was going to go for our observer S prime. So to get L prime, they would do the same thing. They would say, oh no, this actually happened at that location x2 prime. This actually happened at location, sorry, x1 prime. And so they would say that L prime is x2 prime minus x1 prime. Now how does that compare to L? Well, we can put in the Galilean transformation for this. x2 prime would be equal to x2 minus vt minus, same deal here, x1 minus vt. Hey, check it out. The negative vt's cancel. We get x2 minus x1. So we get that L prime is equal to L. So this is also invariant. Under the Galilean transformation. Alrighty. So maybe to make this a little more concrete, can remember what we were doing in mechanics. So for instance, let's say you had two balls and they were colliding elastically. So we'll say that U1 initial for this ball is 2 meters per second to the right. And we'll say that U2, so that's U1 initial, U2 initial is 4 meters per second to the left, so negative. Oops, here, let's do that. Okay. And, if you're a little shaky on doing your elastic scattering problems, it might take you a while to remember how to do them, but there's a trick that we could do. We could boost, that's usually the term you use for transforming to a different frame. we could boost to a frame S prime. Oops, let's make that a little better. We could boost to a frame S prime that is moving at 4 meters per second to the left. Now remember, for an inertial observer, they always get to say that they are the ones standing still and everyone else is moving around them. So to S prime, what this is going to look like is U1 initial prime is 6 meters per second to the right, and U2 initial prime is 0. And this is a lot easier to solve. If you're in a frame where one of the objects is stationary, it's a lot easier to do the simultaneous energy and momentum conservation to get the final answer. Let's say after you do that, so after you crank the numbers for whatever the masses of these are, you end up that afterwards U1 final prime is 3 meters per second, and that U2 final prime is going to be 9 meters per second. Okay, but you're not interested in what S prime thinks it is. You're interested in what U prime, or you're interested in what S thinks it is. And S is saying, oh wait, S prime was moving 4 to the left. So if they're seeing it going 3 to the right, it means in my frame it's really going 1 to the left. So here we can do that, reverse the primes, reverse the signs thing. And we can say, all right, U1 final be U1 final prime plus V, that's 3 meters per second, plus a negative 4 meters per second is negative 1 meter per second. And by the same token, you can say U2 final is U2 final prime plus V is 9 meters per second plus negative 4 meters per second. Remember, we're carrying these minus signs because it's going to the left. It's a velocity, you have to carry the signs. So it'll be 5 meters per second. So then at the end of this, S would say, okay, after the collision, U1 final is negative 1 meter per second, and U2 final is 5 meters per second. In doing this step where we boost into a frame that makes one of them stationary, that made the math for solving the elastic scattering much easier, and then we can boost back into the frame we actually care about. At the cost of doing these two boosts, we got ourselves a lot easier math, and overall the whole process was probably a little easier. Okay. So here's where we run into problems. So if we recall, oops, sorry about that. The Maxwell equations predicted the existence of an electromagnetic wave. And this just popped straight out from the equations. We didn't have to set up any sort of a hypothetical circumstance or anything like that. We just stared at the Maxwell equations and out it popped. And we also had the prediction that here it's verified that the speed of these electromagnetic waves would be the square root of 1 over square root of epsilon naught mu naught, which is just a titch under 3 times 10 to the 8 meters per second. All right, so here's the problem. Newton's first law, which gives us the whole from which the whole Galilean transformation thing starts to pop out, says effectively that all inertial observers have to have the same laws of physics. Or another way to put it is there is no special observer. Now, sometimes there are special observers. I mean, for instance, with sound, when we talk about the speed of sound, there is a special observer. The special observer is the person who is stationary with respect to the air. They're the ones who are going to say that a sound wave travels at 343 meters per second, depending on your altitude, depending on temperature, etc., etc. But they're the person who's going to say what the speed of sound is. And then everybody else, if you do like a Doppler shift calculation or something like that, what everyone else has to do is boost over to the frame of the special observer, do the calculation, then boost back, a la what we just did before. So, but the thing is here, the speed of light just plain popped straight out of the Maxwell equations. So, the issue here is that if the Galilean transformation is true, the Maxwell equations can't be true, and vice versa. So at first, people, because of the history of how the Maxwell equations were developed, and people were thinking of the electric and magnetic fields as these vortices within this hypothetical medium called the luminiferous ether, which we have shown doesn't matter, doesn't exist, doesn't matter. They were able to push the analogy and say, well, maybe the Maxwell equations are only true in the special frame of the ether. Well, astronomical observation was already starting to make people really uncomfortable with this. Here's what's going on. So let's look at the sun. And we'll have the Earth orbiting the sun. Okay. What people realized pretty quickly is that the sun would have to be almost at rest with respect to this ether, possibly even completely at rest. And the reason is, let's say it wasn't the case. Let's say that the sun was moving through the ether, let's say going up, then the ether would see the sun would see effectively this ether wind pointing down. But what would that mean for a ray of light coming out from the sun? Well, what that would mean is it would hook around like that as it's getting blown by the headwind. So in a really bad scenario, it would be the case that almost always the sun's light is getting blown away from us. So this wind can't be that strong. But it turns out it has to be even weaker than that, because even in the situation I've drawn here, if you were standing at this point in the Earth right there, as the Earth is rotating around its axis like so, you would say that roughly this is 9 a.m. But noon is when the sun's overhead, but you would be seeing the overhead light of the sun coming at you at 9 a.m. Sorry, not 9 a.m., 6 a.m. So you'd be looking out at 6 a.m. and basically saying, oh, gee, it's noon. That's a problem. And careful astronomical observation has shown that no, we're not seeing the time of noon being messed with in a way that would be consistent with there being this ether wind. So, if there was an ether, we would be basically having to be stationary with it. Now, you can repeat this entire argument if you don't want to mess with this hypothetical ether, whatever it is. You can repeat this entire argument based entirely around the notion of how fast is the sun moving with respect to the hypothetical special observer that you would have. So workers at the time were postulating that there was a special observer, but already the astronomical data were making people feel really queasy about this. All right, so then that means that if the sun has to be basically stationary with respect to the ether, then it will be the case that the Earth will, as it moves around the solar system, no matter how the Earth is moving, there should always be a headwind of ether coming from the due to the Earth moving through this ether that is basically stationary with respect to the sun. So this is something that's testable, and it was tested in Chicago. The experiment is called the Michelson-Morley experiment. And this was really tough to do. Now that we have lasers, you can do this on a tabletop. And it doesn't cost a whole lot of money or to do. You can just buy little Michelson interferometers, set them up, crank them around. It's great. But at the time, because they didn't have lasers, they had to make the experiment much larger. So the thing was a good couple meters in diameter. They had to have banks of mirrors making light run back and forth across the diameter multiple times in order to take vibrations out on something that large. They had to put the whole experiment on a slab of granite, float it on a pool of mercury. It was a pain. But we have lasers now, so I'm going to describe how you do the experiment with lasers. So here's a laser. So it's a coherent light source. So the light beam coming from the laser will come, and it will strike a partially silvered mirror. So what this means is that half the light will get reflected. Oh, that's awful. Half the light will get reflected, and half the light will pass on through undeflected or unaffected. And then at each of the arms of this experiment, you have a mirror fully silvered. And again, so this will reflect the light. And again, half the light will pass through. Geez. There we go. Half the light will pass through, and half of it will bounce back onto the laser, which we don't really need to think about, although you use it for aligning the experiment. And similarly here, this light will bounce back. It will hit the partially silvered mirror again. Half of it will bounce, like so, and half of it will pass undeflected and strike back onto the laser source, and again you use that to help align the experiment. Now you very carefully rig the experiment up so that these two arms are both the same length L. And you point this arm into our ether wind. So what's going to happen here? Well, the deal is that if there is a special observer, then the time it takes for the round trips will be different. So here, the speed of light here, if there is a special observer, which there's not, but if there were one, the speed of light here would be reduced by the speed of the ether wind. And then on the return leg would be increased by the speed of the ether wind. And if you remember those problems from mechanics where they say, Joe Bloggs is driving down the freeway for the first half of the distance at 50 kilometers an hour and the second half of the distance at 100 kilometers an hour, what was the average speed of Joe? And you discover that it's less than the average of those two, less than 75. So here, the average speed for the round trip is less than the speed of light in a vacuum. This one's a little trickier, but it turns out that here, the average speed is greater. This is because it's an ether crosswind. So because of the whole Pythagorean theorem thing, the speed of the light is going to be equal to the speed of light squared plus the square of the speed of the ether wind. Take the square root. So that's going to be greater than the speed of light in a vacuum. So what this means is this round trip here is going to take less time than this round trip here. Thus, this one will take more time. What this means is that because the light was coherent to begin with, the crests of the light waves were in sync here. The crests will no longer be in sync here. So if I put a screen here, and then I go look at the screen, what I'll see is an interference pattern. And so what Michelson-Morley had done was they had rigged up the distance of those arms L such that if, say, they saw a dark interference minimum in the center of the interference pattern on the screen, and then they rotated the entire apparatus 90 degrees so that the ether wind would be coming down this way, and this would be the crosswind component. So they're reversing which one is the which one takes more time, which one takes less time. If you reverse that, they had it rigged up that, say, if you're seeing a dark spot in the middle of the interference pattern before, you would see a bright spot in the middle of the interference pattern. They did the experiment, and there was, so after the whole thing was rotated 90 degrees, there was no shift in the pattern. And the only conclusion you could have from that was that for every part of the trip, regardless of whether you're going in the headwind or the tailwind, the speed of light was the same. So the conclusion is that all observers had to measure the same speed of light. So, going back to what we had before, this also means that the Galilean transformation is incorrect and will need to be modified. We will replace that in the next lecture series with the Lorentz transformation. And here's how we know it's incorrect. Let's go back here. So if you imagine somebody who had a flashlight and they happen to be in a very fast car going past you, let's say they're driving at a third of the speed of light, they go ahead and they turn on their flashlight. You would think, well, okay, they're heading, they're heading away from me. So if they're measuring the speed of light for that and they're heading away from me, I should be measuring that light going at 4/3 c, but that's not what happens. Both u and u prime are c, the speed of light. If it makes you feel any better, they disagree about the color of the light, but they both measure the exact same speed of light. So this lends support that, yes, indeed, the Maxwell equations are true for all observers. And it also leads to the conclusion that the Galilean transformation is incorrect. That also means that it calls into question all of the invariants that we calculated. Like, for instance, here, will the two observers agree on the same length? We don't know. The Galilean transformation was shown to be incorrect. It could well be, and in fact will be the case, that the two observers will disagree on the length. What about the acceleration of something? Again, same problem. Even what about the time? Just remember, we just sort of implicitly said that t equals t prime. We're going to have to re-examine that even. So, and that's where we're going to start looking at the issue of simultaneity. Can we have it be the case that if two events happen and one observer says they happen at the same time, would another observer agree on that? 10 A T E I T Y. All right. So at this point, you're probably wishing that there was a couple thunderbolts coming down from the heavens and taking me out. So let's roll with that idea. So let's say we're on some hypothetical very fast train car, or actually I am right here. I'll call myself O prime. So let's say this is point A here, point B here. So here's U, and I am going, as you see it, really fast, a substantial fraction of the speed of light. So here's U standing by the side here, and you see the most wonderful, amazing thing. You see lightning bolts simultaneously zap me at both A and B. So the question you should ask the first question you should ask yourself is, and I'll call you O, is did I, O prime, see the two events at the same time? So go ask yourself that, and we'll get back. Okay, so you should have convinced yourself that yes, I definitely saw B happen before A. Since I'm moving this way, I'm running into the light from B, I'm running away from the light from A. It's going to take more time for the light from B to so it's going to take more time for the light to make it to my eyes from A than from B. So I would see B before A, definitely. Here's the next question, though. Did I, O prime, observe B to happen before A? Okay, and the answer to that one is yes, I did. I observed B to happen before A. So you say A and B same time. I say B before A. Technically, I should probably call it B prime. And why would I conclude that? I would conclude that because, let's say I was trying to suggest I was equidistant to the rail car, but even if I wasn't, that wouldn't change it. It would just complicate things. So let's say I'm equidistant to the rail car. I saw, we all agree that I saw the light strike my eyes from B first. And then the light struck my eyes coming from A prime. Okay. So we agree that I definitely see that, but why would I observe that? Because remember, as an inertial observer, and everyone who's moving at constant velocity is entitled to say they're an inertial observer, all inertial observers are entitled to say that they are stationary and all the events of the world are happening around them. So as far as I'm concerned, I'm stationary. If I saw B prime first, and I know that these two distances are the same, right? So since I know the two distances are the same, I know it takes the same amount of time for light to travel from B to my eyes as from A to my eyes. So in this case, I don't even have to do all that tedious math. I can conclude that yes, indeed, B happened first, then A, because I saw B and then A, and I know they had, me seeing the events had the identical time of light, speed of light propagation delays. Okay, but you definitely said that A and B happened at the same time, so how would I explain that? Well, I would look at you and say, all right, well, I definitely know that B happened first, and then A, but you, observer O, you were moving to the left at speed V. So you were running into the light coming from A. You were running away from the light coming to B. So you ended up like over here or something when it just happened to work out that the the advantage of the head start of the light from B just happened to work out that the light got to you from B, thanks to the head start, at the same time the light got to you from A. So we would agree, so we can both predict what the other person would observe, but we would conclude, we would have to disagree on which event happened first. You would say they happened at the same time. I would say that B first, A second. We can each predict what the other person observes. Now, just a quick thought going back here. Remember our constraint on measuring the length of something. To measure the length of something, we need to have the firecrackers going off at the same time. Well, we're not agreeing on that anymore. So because we're not agreeing on that, it'll churn out that we'll be disagreeing on the length of that rod. But that's for the next video in this series. Okay, so I want to be clear here. This isn't an appears to be, or somebody's under an illusion, or somebody's really right, or something like that. What is happening is you and I are having different experiences of space and time. They are both correct experiences. It's not like one's the real one and another one isn't. But we are having different experiences of space and time. So in the next video in this series, we will figure out how our experiences of space and time differ, and I'll catch you on that one.